Howdy folks, welcome to week 4 homework. We're going to be taking a look at regression. Some of this stuff is going to be fairly familiar for the folks who have taken me before, so once again you might be able to skip around on this video. Regression, we've looked at it just a little bit so far, but we're going to start off here today taking a quick look at exactly how it works, a bit of a refresher if you've missed any of the classes or have forgotten some of the class stuff that we've talked about so far. Let's start off by just doing a regression. I'm going to go ahead and pull up Jamovi and get the air quality data set going. So we'll use the RStats air quality data set, go to open, make sure you're in the RStats folder, get that air quality data set, and let's run a regression real quick just to show what we get. Let's put ozone as the dependent variable, solar radiation as the independent variable. By default, it's going to give us these two outputs. These two outputs mirror here what we've got on the PowerPoint. So I'll talk through it if you want to take a look at that more so later. Maybe I'll let you pause here if you need to look at this. Basically, we have a model fit measure. This shows us how well the whole regression explains the dependent variable data. We'll get an R and an R squared. The R squared is usually the effect size for regression. R here of 0.34 is kind of low, so the 0.121 for regression is also kind of low. To tell you, just looking at my chart here, 0.01 is considered a small R squared, 0.09 medium, and 0.25 large, so this is kind of in the medium range. I would still look at this R squared and not be particularly happy with it. For me, medium range would probably be around 0.4, and the reason for that is that it's actually not too hard to get higher and higher R squared values. We'll see that over the course of the semester. Now, you do not have any way to check if the overall regression was significant by default. To get that, you go over to the model fit and ask for the overall test. You'll see this is basically an ANOVA. It reports just like ANOVA. The only thing that's different about it is that the effect size is an R squared. The other output you get are the model coefficients. And so what these are telling you is there a significant effect of any one or multiple of the independent variables. You also get an intercept here. The intercept is not a type of independent variable, but it allows you to build a regression formula. We've seen that a couple times in class, but I'll go over it here just quickly so that you can solidify your understanding. When you are looking at the output for those coefficients, you can report them just like you would a t-test. If you want an effect size, you can report this. This is the number you would put in the regression formula, but it is in the scale of the variables that you're dealing with. A little bit of a scale-independent version of that is this standardized estimate. This is a little bit more commonly considered the effect size for that. Another thing you can do is go to the ANOVA test and you'll get F and P values, and this is a little bit more interpretable in terms of effect size that you've dealt with before. It does not allow you to get an effect size here by default, but using the mean squared sum of squares, you can actually math out the eta squared for the independent variables if you like. Okay, so what is the regression equation? Well, anytime you run a regression, or anytime you run any sort of the statistics that we've run so far, what's actually going on is your analysis tries to create a line that fits your dependent variable data as closely as possible. That line is created using a formula that looks like this. This is kind of an extended version of the formula you might have learned in high school or middle school, y equals mx plus b. The b0 here is kind of the b part in that formula that you learned in high school. This is the intercept. It tells you if all of your independent variables are 0, where is your line starting? Where does your line intercept the y-axis? And so this B0 is going to be that intercept estimate right here. You'll notice this does not have a standardized estimate, and that's because you're really not intended to interpret the intercept as an independent variable or try and compare it to these others. The standardized estimate is all about comparing independent variables to each other. This number here, 0.0127, tells you that for every 1 point increase in solar radiation, there is a 0.127 increase in ozone. And so if you had a formula, you're trying to create that regression formula, it would be y is equal to, I'll put it here so you can see both, 18.599 plus 0.127 times solar radiation. And that's it. That would be the whole formula. The reason we've got this b2, x2, and an ellipse is to show you that you can continue making this formula for any number of independent variables. The last part here is your error term. Usually that's not actually included in the formula, but it's there in this sort of theoretical representation to make sure you remember that this is not a perfect formula. If we go over to the regression and ask for a graph, you'll notice that by default it's going to have these gray areas in the graph, and that shows you the range of, well, here's my prediction line, but the data could probably actually be anywhere in this area. There's a module called that lets you make scatter plots. If I just go find it, let's see if I can get it. Maybe if I just look at the installed ones. FlexPlot is not bad, but Scatter is the one that lets you make just quick and easy scatter plots. If we do that, we can make a regression where the x-axis is solar radiation, y-axis is ozone, and we can add in a linear regression line. So this line is actually the same as this line over here. You can tell it starts around the 20 mark and ends 300 is about at 50. So starts at around 20 mark, 300 is about 50. So this is actually the same line. If we include standard error, it's going to give us the same grayness, but the scales on this are different because it shows you all of the data points, and you'll see that actually not all of the data points are adequately measured by a regression line. So how many data points would you say are not measured by this regression line? Definitely there's a big heteroscedasticity thing going on over here because there's a lot more variance here than there is over here. So if we look back at the regression, this R square value is telling us that solar radiation accounts for 12% of the variance in ozone. Does this look like we're accounting for about 12% of the variance? It does look like that to me. Okay, so we've seen how you can use a regression formula. If you'd like, as part of your homework, I believe, you'll need to try to use that regression formula to actually make a prediction. I'll just do it one time here for you. I've already got this stuff set up, so I won't have to type it out. But what this formula might look like is, all right, your y number is equal to, and we'll just pop in those data points from the intercept and the things here. Y is equal to 18.599 plus 0.127 times x. Okay, and so let's fill in our x. Right now, by default, x is equal to 0, so 18.59 is our prediction. But let's go get a data point. So our x is equal to 190. We put x equal to 190. It predicts 42. That's pretty close. Let's try a different one. I know that on this higher range, things are going to be a little bit wilder, so we'll find about 290. Is y pretty close? 290 says the ozone would be 11, and it predicts 55. Not quite perfect, so there's definitely some wild stuff going on there, but it's not the worst regression of all time, and it definitely did come out with a significant effect. So I showed you that just so you can be aware that even if you get that significant regression, depending on your R square value, you might get a pretty dang radically inaccurate regression formula. So if what the formula predicts is what you're interested in, you got to be really, really careful. If you're just trying to see is there a relationship there, well then maybe that effect size is not as important as the significance. It's kind of going to be up to you. How does the regression formula come about? Well, just to show you quickly what these points are, we've got our y and our x variables, so x here would be the highway miles per gallon, y would be city miles per gallon. If we add in a line, that's what our b and b1s are going to do, and the error is kind of this range of data that we were looking at before. If we manipulate our intercept, the line is going to, let's make sure we label that. If we manipulate our intercept, line is going to go up and down. That's pretty much the only thing that's something that gets added in, like the intercept can do. If we manipulate our b1, that's the coefficient for the first independent variable, the slope of the line is going to teeter-totter like that. Sorry, the range there is not perfect. So how is this regression line produced? Well, you really don't need to worry about that too much because your statistical programs are going to do it for you. But if anyone ever asks, what's going on is some procedure based off of a method of least squares. And what the method of least squares is a style of fitting data to a formula based on minimizing the distance between the line and the actual data. So it's actually trying to get the least squared error in your data compared to the line. If you would like to learn a little bit about that, I really wouldn't recommend trying to learn exactly how it works because it is pretty dang close to computational magic. If you want to get started, I would say take a look at this standard deviation formula. X is just an X thing. X bar here is the mean of X, N is the sample size, and see if you can work out how we get from the data points to a standard deviation. We've already learned what a standard deviation is, and then you can kind of guess using these formulas how you might try to minimize the standard deviation by adding in a prediction line there. But honestly, that's too much work. It's better to just continue assuming that this is magic. Okay, so another thing that it's good to learn is that you can actually include categorical variables in your regression line. Part of the thing is that in a regression, you pretty much should only be using continuous variables. So how are we going to include a categorical variable? What's actually done is something called dummy coding, and the way it works is it takes all of the levels of that categorical variable and just considers them to be different possible intercepts that we're working with. So you just add a different number based off of the different levels. So in actuality, the regression line might be on average here, but condition 1 would be this red line, condition 2 blue, condition 3 green, and so the regression line moves up and down depending on what happens. So to summarize, a categorical variable in a regression has to be dummy coded, and it adds something to the regression prediction. A continuous variable can be added in as a multiplier to the coefficient for that variable, and it multiplies to change the results. Okay, so we've already talked about the output that you get from the regression, and I've quickly gone through what dummy coding is. If you'd like to learn more about that, we can, but I'm trying to keep this really quick and succinct, go through a lot of information very quickly. Okay, so what is a regression actually doing? Well, when you run a correlation, you know that what's going on is you're seeing how much overlap in variance is there between your independent and your dependent variable. So when you look at these data, if you run that, this is kind of what a correlation looks like. What you've got here is some covariance, your variables work together, and you have some unaccounted for variance. This is the variance in your dependent variable that your independent variable cannot explain. This is the same thing that's going on in a simple regression, but things get more complicated as we get to more complicated multiple variable regressions. Suffice to say that if there's more covariance, you have a higher R squared, more significant relationships there. If we look at a regression with multiple variables, what actually happens is that the significance of every individual variable in that regression is only based off of the unique covariance it has with the dependent variable. So in this graph we have independent variable 1, 2, and your dependent variable. How significant independent variable 1 is a comparison between unique covariance of independent variable 1 and the unaccounted for remaining variance of the dependent variable. This area here, where independent variable 1 and 2 both account for dependent variable variance, is ignored completely. This is because your independent variables are supposed to be independent of each other. So when you run that regression, any overlap between these independent variables is going to be ignored as error. Therefore, including more independent variables can sometimes make one or the other independent variable not significant because they overlap too much. Another point of this is that, this just the slides show that a little bit better. Another important point of that is that if you add in more and more independent variables, the amount of unaccounted for variance is always going to keep going down. The more variables you add in your regression R squared can either stay only exactly the same if your new variables did not do anything, or it can increase your R squared. So a pretty easy way to cheat when you're running your regression is to add enough variables that your regression becomes significant. Do you have a meaningful regression there? Not necessarily. Is your R squared being big something that really was valuable? Not necessarily. You could have just chucked enough stuff at the wall and until something really stuck. Now, we're at the 16-minute mark, so I think we can try and quickly cover the regression assumptions. There's quite a few of them, and they're a little bit complicated, so I don't want to go into them in too much detail. Let's just cover them very quickly. This is just a picture of the regression assumptions available in the optional assumption checks area for your regression. What do each of these regression assumptions do? Well, we know that a QQ plot is going to check for normality. It's a little special because the normality we're looking for is normality of residuals. Basically, what we're checking for here is homo and hetero skedasticity. Does your regression line have similar predictability across the entirety of your independent variables? That's why we have a QQ plot, not of the data to a normal distribution, but of the residuals to a normal distribution. Residuals are the distance between an actual data point and the estimated data point from your model. We also have residual plots, which pretty much do the same thing. They try and show you how close or far away your data are from your regression line. So let's quickly take a look at that. QQ plot of the residuals shows us that in the low end of our independent variables we have higher residuals, in the middle we have lower residuals, and at the upper end we have higher residuals. And you can kind of see that here. If you go back to the scatter plot here, so here we have a little bit wider space than we do kind of in this middle area, and then here it kind of goes off the rails. The residuals plots shows us, okay, how bad is our prediction line compared to our error, and really what we're looking for here is that we just have random points. This is pretty obviously negatively correlated, but it's not too strong, and there definitely seems to be kind of a triangle shape there. So there's something unusual happening here, which is not a surprise given the triangle shape that we have here. There's more error going on this side than that side. If we look at the residuals plot based off of the x-axis here, is going to be the dependent variable. You see that the error is much lower here on this bottom end and much higher here on the top end. So if we follow the prediction line and try and think of this as that x-axis, you can tell that at the highest end we have the least accurate predictions. Finally, the residuals based on solar radiation as your x-axis looks a lot like the fitted residuals. The difference between these two is non-existent at this point because there's only just the one independent variable. So these are the residuals for the whole prediction. If you had multiple independent variables, then this graph would pretty much be the only one you have to look at. But if you're particularly concerned about how well one or another variable is getting worked with, or not, then you would look at these individual graphs. Because this is the only independent variable, graphs are the same. So what are these other assumptions that we've got? Well, the autocorrelation test is kind of a test of independence of variables, and so is the collinearity statistics. The autocorrelation test is one that checks for how independent is the dependent variable results. So remember when we were talking about repeated measures ANOVA, we needed to do a repeated measures ANOVA because within the dependent variable there was a relationship, and those relationships in the dependent variable can cause a faulty analysis. The way that you check the autocorrelation test is it's literally just a test here. And in this case, significant result, no bueno. More often than not, that's not as important as just looking at this DW statistic. So how do we interpret this? I'm not going to require you to memorize that information. I'm actually just going to give you here a bit of a cheat sheet that tells you what do the different assumptions mean and how do you interpret them. So if we go over to autocorrelation right here, this is systemic error in measurement. What does that mean? Well, why would your why would your dependent variables have a systematic set of errors to them? Why would they be associated to each other? Well, maybe you have a repeated measures variable. Maybe you sent out a researcher to go collect data based off of their observations, and if that researcher consistently observes overconfidently, that set of data is going to be related to itself. So you're going to have an independence within your dependent variable problem. You're going to have an autocorrelation problem. Usually, for any statistical analysis, a significant assumption check is bad. But for the most part, as long as your autocorrelation DW statistic is between 1 and 3, you're perfectly fine. And we can see here in this example, we have a significant test here, so it's probably not great. And it's significant because the DW statistic is close to 1.1. So that tells us that there might be some sort of inconsistency going on, or sort of consistency and error in this ozone dependent variable. And we can actually see that because this is not a randomly distributed residuals graph. I fully expect that if I go get a scatter plot, a histogram of my ozone, I probably will see some funky stuff. And yeah, there we go. So here's your histogram of ozone. It's not normally distributed, so there you go, that's what's going on there. But because the data point's between 1 and 3, it's just not bad. Could be worse. Collinearity is a simpler thing to understand. That basically means, are your independent variables independent of each other? So the way you check that is with a VIF number. As long as you have a VIF number less than 10, you are good to go. So if we go back to our regression, check for collinearity. Go find that collinearity check. Here we go. It's called collinearity statistics. Your VIF number here is 1, definitely lower than 10, so you're good to go. Why is it a standard 1 here? Well, it's because we only have one independent variable, so of course the independent variables are independent of each other. I'm just going to pop in another one here just to show you how this might change. So now the VIF number has gone up because these two variables are related to each other a little bit, but we're still far, far from 10, so this would be fine for that. Okie doke. Last one is Cook's distance. Cook's distance is this form of outlier check. Now, normally, when we check for an outlier, like if we look here, we're looking for a data point kind of like this one, where the data point is far removed from the rest of the data. However, in Cook's distance, we're checking for an outlier associated to the regression line. So instead of an outlier that's unnecessarily big, we're checking it for an outlier that is surprisingly far from the regression line. Now in this case, that outlier, this dot here, is going to be the same one. But there are certain situations where an outlier just in the data might not necessarily be an outlier for the whole regression graph. For example, if you had very few data points, if this was like 1/20th of your data, this regression line would be much closer, something like that, to it. And so it would not have a particularly far distance from the regression line. And so its Cook's distance would be pretty low. In this case, I can assure you this Cook's distance is rough. So let's go back to our regression and ask for Cook's distance. We'll find the Cook's distance data. Here we go, Cook's distance. And this is given to you as kind of a set of descriptive statistics. Why? Because you can actually get a Cook's distance for every data point in your regression. There's a Cook's distance for each one of these. And all we really care about is what is the worst Cook's distance looking like. So the minimum and maximum Cook's distance is what we care about for the most part. So the minimum Cook's distance is very, very, very close to 0. So that means that there's one data point that's practically on the line. Fine, great. The maximum Cook's distance is more often than not the one we care about. How bad is the worst data point? So in this case, the worst data point is a Cook's distance of 0.09. What does that number mean? Well, let's just go over to our cheat sheet again. Let's check out Cook's distance. A Cook's distance of 1 or greater is bad. So 0.09 is not bad enough to be considered bad to the bone. So in this case, we're totally cool. That doesn't mean that you don't have an outlier problem. It just doesn't mean that you have an outlier residual problem. So if we look at these residuals plots here, this point is not necessarily that much far off worse than all of the others. It is maybe a bit of a troublesome point here, but again, it's not too bad. Really, the bigger problem here is the normality of the distribution, not the outliers. Okie doke. So we've already talked about this slide. Just to restate, adding more variables to your regression is always going to increase your R squared, and that's always going to increase your chance of type 1 error as well. So one of the ways you can cheat with your regression is to just keep adding variables till things work out. Another thing that you can do with your regression is manipulate the variable types. So we've learned so far that continuous variables have more variance, and so they will tend to be more significant than categorical variables. And since we're talking about dummy variables, those categorical variables in your regression, you might not be surprised that if you add the same data point as a continuous or a categorical variable, you're going to get a different set of results. So just to show you here, let's play with the month. Month is a ordinal variable, which means that it can be considered continuous, or it could be considered categorical, kind of depending on how you want to work with it. So if we put month here as a categorical variable, I know it's called factors. It really just means a categorical / dummy variable in your regression. You're going to get, let me just show you. Let's walk through what this actually says, because this is a bit confusing. I don't think I've explained it. Here's what your dummy variable looks like. What's going on is it's set up a series of pairs of comparisons. So it's actually turned this variable that has 5, 6, 7, 8, 9, 5 different categories into a series of 1, 2, 3, 4 continuous variables. The way you would include this in your regression prediction formula is, instead of multiplying this number by anything, you just add this number. So if you are in month 5, you don't add anything. If you are in month 6, you add 5.8 to your formula. Month 9, you add 7.8 to your formula. If you want to interpret the significance of the overall month variable, you're going to have to get a different output, because you'll notice there's a significance of each one of these individually. This is kind of like doing a t-test. Does the difference between month 6 and 5 matter for ozone? And it is literally doing a t-test. 6 and 5 are not particularly different, but you'll see that 8 and 5 are significant because there's a difference of about 36 points. If you want to check for the overall significance of the month variable, you'll go over to the model coefficients and ask for an ANOVA test. And there you go. You basically get an ANOVA for the dummy-coded categorical month variable that you can report just like you would report any other variable. If you have continuous variables in this data set, they will also appear in this ANOVA test, so it may be easier to report this stuff if you just want to report the overall variables instead of the estimates. That's a choice that you need to make yourself. Okay, back to the discussion on categorical versus continuous versions of the same data point, because we're at the 30-minute mark. I want to wrap it up. Here, the ANOVA says that we have an F of 8.5, and that's pretty dang significant. We take this month variable, pop it in as a covariate. Now the F has gone down, and it's stopped being significant. Now, why would this kind of be the exact opposite of what I was saying? Probably in this case because months encompass a much wider range of data than what your normal categorical data points would cover. And so you can have month-to-month variance that's a little bit more meaningful than the month as an order of variance. Sorry, this example could be better. In general, I will repeat myself, a continuous variable is going to be more significant than a categorical variable. However, as you can see, there will be some cases where that's not necessarily true. At the very least, you can tell that there's a big difference in the significance of this month variable when it was continuous versus categorical. And just in real life, I can assure you that the order of the months isn't always that important for the weather, but you can summarize a whole month a little bit better than you can summarize the order of the months. Yeah, this could have been a better example, but I hope the point is getting across. Now, I kind of perceive that this would have been a bit too much stuff to cover in just the 20 to 30 minute video, so I'm not going to walk you through reporting a regression. I am going to show you here just very briefly a couple of slides based off of a couple regressions. This is the information you need to run a regression. You're not yet going to really be working with multiple independent variables, but it'll just show you your options, because a lot of what we're going to be doing with the regression is kind of the same stuff we've done with the multiple variable ANOVAs. So I'm just going to show you some reports for the regression, so you can pause the video in the next couple of moments, see the differences between here a long form regression report. We have a lot of data in those regression reports, so there's a lot that you can talk about. There's also much shorter versions of those reports, and sometimes this is what people do. They just give a very simple, quick, dirty thing on what happened, and this doesn't tell you everything that's going on. Maybe adding in a graph would be helpful, but in all honesty, if this is all you need to say, then this is all that you need to say. How do you choose what you want to focus on in your regression? There's a lot of different options, and it really depends on what research questions you're trying to answer. I would always encourage adding in a scatter plot with the line, but that's not always going to be what you're trying to show. In all honesty, if you are just saying, okay, well, there's a relationship between one variable and the other variable, and we got a regression formula out of it, if you show a scatter plot with a line, something that looks a little bit like, I guess, this guy down here, people are going to go, well, yeah, that's a relationship, and that's a significant regression, but boy, does that kind of suck. Look at all these data points that aren't being accounted for. And so one thing that you have to be worried about is if you post that graph, you're not really going to have a very convincing argument. But if you just get rid of those data points, maybe post a graph that looks, where was it? Or maybe just post a graph, I see, post a graph that looks like this. This is going to be a lot more convincing, because it's like, oh, well, okay, as months go on, ozone goes higher, great. There's a lot of different options that Jamovi gives you for running the regression. I believe we've covered all of these already. And once again, just going to finish off here with something you can pause if you want to read this through. This is a regression report that I wrote for one of my own papers. There's some stuff in here that could be a bit better, some stuff that could be a bit worse. Okay, guys, that's going to be it. I've gone a little bit over time. Sorry about that. Hope I haven't gone too fast. There's a lot of material in this video, so you may need to watch it over and over again to get what's going on. Have a great week, and take it easy.